Hi everybody, we are in 6.2 and in this particular section we are going to be looking at evaluating logs. So we've already done this, but we're going to look at this when it's presented in a slightly different way. So just a reminder that if I give you an exponent, for instance, that I can rewrite it as a log. So if this is my exponent problem, the first thing I have to remember to do is write the word log, and then the base of the exponent is the base of the log. That's that little sub number, right? And then I jump to the other side of the equal sign. The 8 follows it, and then I jump back over and I write equals 3. So this is the exponent version. This is the equivalent log version. They both tell me the same thing, all right? Now, let's switch spots. If I give you a log, right, so if I say, then what I can do is give you the exponent. So again, what I do is I start with the base of the log, that's the 4, jump to the other side, that becomes the exponent, and then jump back across the equal sign and 16, because 4 to the second power is 16. A couple of other things, just as far as the vocab goes. I want you to remember that b is the base and x is called the argument. And what we will, again, we'll focus on when we get into solving more. But this base, just like the base and the exponent, for graphing purposes and everything, that b has to be bigger than 0, but it can't be 1. So what we actually said is that b is bigger than 1, and that's growth. And when b is in between 0 and 1, that's our decay form of log. So these two together are just saying this, all right? But I think if this is how we've talked about it first, that makes more sense. The other thing that we have to talk about is that the argument in a log is never 0 and it's never a negative number. So what this is saying is that the argument is always positive. So the argument, I don't think I spelled argument right, I think it needs an E in there, is always positive, and that's going to come into play here. And unfortunately, I'm not going to go into detail as to why that has to always be positive. We'll follow that up in our next section with when we start solving. All right. So we're still evaluating. We're still doing this stuff. All right. But we're just going to look at it a different way. So in all of these, we're going to evaluate a log, but you're going to have to create the problem. So just a reminder, we are going to do all of these. That if this is my function, f of x, and this is the actual function, this says put 4 where the x is in the function. So I'm going to write it down here. And basically all you're asking yourself is 2 to the what power makes 4? And that's a 2. So f of 4 is worth 2. Or if I write this one, what I'm asking myself is 2 to the what power makes 8? And that's a 3. And remember, I did give you that exponent table where you could be looking right now at 2, and 2 to the what gives you 4, 2 to the what gives you 8. Actually, I think you looked across. So let's write this one up. So 2 to the what makes 1/2? Well, remember, a fraction comes from a negative exponent. So that makes my fraction. So now I'm just asking 2 to the what makes 2, and that would be a first power. Let's put this one in. This is one of those important logs that I just hope you always remember. It doesn't matter what you take, what the base is of the log. Whenever you take the log of 1, you're always going to get 0, because 2 to the what power gives me 0. Well, something to a 0 power always gives me 1, and I think I said that wrong. So this is actually 0. So 2 to the what power makes 1. That's a 0 power. A 0 power always gives you 1. All right? So let's take a look at this one. So 2 to the what power will make -1. So this is this thing that I talked about here. The argument is a negative number. This argument, the x, has to be positive. And so I guess one thing I could show you is if I did put an exponent in there, 2 to the x, and you start looking at a table. So let's see, can you see that? So, 2 to the negative power, 2 to the negative 2 power is a decimal. 2 to the third power is 8. And what's going to happen is negative exponents, remember, don't make negative numbers. They make fractions, and these fractions are just decimals. So the only thing that you're going to see happen is you get a smaller decimal. So when you see something like 1.5 e to the negative 5, what that is saying is that 1.5 e to the negative 5, that I should move this decimal over 5 times to the left. That's what the negative says. 1, 2, 3, 4, 5. And so this isn't a negative number. This is just a really small number that's not quite 0, but it's really close to 0. So remember, if your argument is a negative number or 0, you will not get an answer. So this is no solution. It's a non-real answer. And then that's what happens here. 2 to the what power gives me 0. Again, if you just look at this table, I'm never going to get 0. These numbers are getting closer and closer to 0, but they're never going to become 0, and they're never going to become negative. So again, this would just be a no solution. So these are just reminding you that the argument can never be a negative number, and it can never be 0. Let's jump over to the next set. This time in our log, our base is 9. So 9 to the what power makes the 9? Well, that's 1. And remember, when your base and your argument are the same, you're always going to get 1. All right? So if you can remember that, great. If not, you think about it as an exponent. So log base 9 of 81. So 9 to the what power makes 81? That's 2. And notice here, our 81 just moved into a fraction. And the only thing that made it a fraction would have been this 2, this exponent, being a negative number. So 9 to the what power makes a fraction of 181? 1/81th? Well, the negative makes the fraction, and then the second power makes the 81. Here we go for this one. And again, what I want you to realize is that your argument is a negative number. That is not possible. Automatically, no solution. You can't take 9 to a power and get negative 3. You can get a fraction, you can get a positive number, but you can't get negative, and you can't get 0. And we're going to leave these out. Let's take a look at some with ln. So just a reminder that ln is a log. It just has a base of e. And so what's happening here is that base then is about 2.7. So they don't write log e, they write ln. It's called a natural, N for natural, L for log, natural log. So if I just put these in, again, all this is asking, and maybe for now it's helpful to write e. E to the what power makes 1? Well, anything to a 0 power is always 1. Doesn't matter if it's 2.7 or if it's 8. And we saw that right up here. 2 to the what power makes 1? That's a 0 power. All right, so what happens with ln of e? So again, it might help to write it like this. So e to the what power gets you right back to e? That would be a first power. So again, when your base and your argument are the same, which happened here, you always get 1. All right, so I did pick 2 challenge problems here. So again, ln of the square root of e, which it might help to write like this. So this one I'm going to write out a little bit more. E to the what power makes the square root of e? Well, I hope you remember that a square root is just a 1/2 power. So what would this exponent have to be if the bases are the same? We talked about this in our last chapter. That means those exponents have to be the same. So our question mark, this whole answer, I'm kind of running out of room, is worth a 1/2. So let's take a look at this one. Since we're not going to do this problem, I'll probably use the space. So ln e squared. And maybe you don't write log e. Maybe just remind yourself that that base is e. So you're asking yourself, e to the what power makes e squared. So e to the what power makes e squared. Again, this just goes back to our last chapter, that if the bases are the same, that means our exponents have to be the same in order for the equal sign to hold true. So if this is 2, that means this equal sign has to be worth 2. So my answer here is worth 2. And then the last one, ln of 0. Again, I'm just going to put the e there. And I'm asking myself, e to the what power makes 0? Well, again, that's like this one. You can never take something to a power and get 0. You can get a fraction and you can get a positive number, but you're never going to get 0. So again, this is saying e to the what power makes 0? Well, that's not possible. We're going to say just no solution. let's jump through these next set, and then we're going to talk about, and again, this was part review. The next part is going to be pretty important when we get into our next section of solving. So here we have two functions. We have g of x, which is 4, and subtracting the log. And remember, when you don't see the base, there's an understood 10 here, so I'm going to smush that in there. And then f of x is just x minus 8. So here we're going to put 1 in. So I'm going to take 4, and I'm going to subtract the log with its understood base of 10. So these are all numbers. This is worth 4, and this is worth something. So what we're going to do is just figure out what this number is worth, and then we can take 4 and subtract it. So as we did over here, 10 to the what power makes 1? Well, 10 to a 0 power. A 0 power always gives you 1. So as it turns out, this is just worth 0, and then I can subtract them and get 4. So now let's put the 100 in. So I still have a 4. Understood 10. And this just is saying 10 to the what power makes 100, and that's worth 2. And so now I'll do 4, take away 2, and get 2. We're going to skip this one. All right? So now I'm going to put a 1,000th in there to think about how to say that. So my argument is this fraction. So 10 to the what power makes this fraction? So remember the fraction, so I'm going to kind of run out of room. So I'm going to put the 4 there, okay? So the fraction comes from, here's the minus sign, sorry. The fraction comes from a negative number. So now all I'm going to ask myself is 10 to the what power makes 1,000? You could use your exponent, your power table, and that's a 3. And when you have 4 subtracting negative 3, that's like you having 4 add 3, so I get 7. So there's definitely a few of these on your test. So these are composite functions, and you should just think of this as silverware. So I think for the first one, I'm going to start here and do the second one and put it over here where I have more room. So I'm going to start with this bottom one. So with your silverware, make those parentheses really big, and this says I'm just going to take g of 10 and work with this function. So I'm just going to go up to g and put 10 in here. So this is all just g. And I've put that 10 in for x. So if you do remember, this is a shortcut. If your base and the argument are the same, you always get 1. Why do you always get 1? Because 10 to the first power is that 10. So that's why you get 1. So when we're done, g of 10 is worth 3. So imagine all of this is just staying in those parentheses, right? And now what you should be seeing is f of 3. Because the f was just hanging out here all the time. And now I'm going to go to f's function and put 3 in for x. So that just means I have to do 3 take away. So when I'm done, my final answer to all of this, which you can't see that, is this negative 5. So I'm going to smush that negative 5 right here now. So let's take a look at this one. So for this one, this says, here's my outer parentheses. I'm just going to look at f's function, and I'm going to put 108 in here. So just f's function right here. And I should put 108 in for x. And I'm going to keep those in the parentheses that I'm seeing. So 108 take away 8 is 100. And now that g that I was ignoring, I'm just going to bring it back. And now this says go to g's function and put 100 in. So I'm going to put 100 in right there. So that's what I'm doing now. And again, I'm not good with logs, but I'm good with exponents. So 10 to the what power makes 100? That's 2. And when I'm done, 4 take away 2. The final answer to all of this, I'm going to write it right up here, is worth 2. So that's just a little bit of review. We did evaluate logs, but the only difference is we had to create the problem, and that's kind of more the format you're going to see when you take your Chapter 6 test. All right. This next part is called inverse properties, and as I've said before, inverses exist in so many different ways. Adding has subtracting, multiplying has dividing. Let me think of some of the other ones. So something squared has a square root. Something to a 4th power has a 4th root. So there are lots of inverses. X has an inverse. It's y. Y has an inverse, and that's x. So what inverses do is they undo each other. They cancel each other out. And what we're going to take a look at is, what if you put a log and an exponent problem together? What happens? Because now an exponential function and a log function are opposites of each other, so they should undo each other. So when you are taking the log of a problem, and when you take the log and that base is the same as the base of the argument, because that's what's in here behind that, then what happens is think of this log b, this log with the base, takes out the exponent with the same base, and once you cross those out, whatever you get left is what you have, right? And you would have seen that in something like this. So if I have 4 to the second power, if I want to undo a squared, I would square root, and this square root would cancel out the 2, and what I'm left with is 4. I hope that makes sense, because 4 squared is 16 and the square root of 16 is 4. So if you have an exponent problem and the base of the exponent, and then in the exponent is a log, so this base is the same as this base, they cancel each other out, and what you're left with is your answer. So we're looking for the bases to be the same, the base between the exponent and the base between the log. So this problem right now is presenting as an exponent problem because it's 2 to an exponent. But the base of the exponent is 2 and the base of the log is 2, so they cancel each other out, and what you're left with is what you get. So here, this one is another exponent problem. This is the exponent, and the exponent happens to be a log. But the base of the exponent and the base of the log are the same, so they cancel each other out, and whatever's left is what I get. And you're always left with something. You're not left with nothing. So in this one, where is the base? Just remember that it's an understood 10, and so this log base 10 cancels out this exponent base 10, and what I'm left with is 5. In the ln, the understood base is e, so the ln e, base of e, cancels out the base of e in the exponent, and I get an x. And just a reminder, these are log problems, they just happen to have an exponent in it. So this is an exponent problem, the exponent just happens to have a log in it. But they both have a base of 7, and when I'm done, the only thing left is the x squared. And again, this has a base of 10, and this little log here has a base of 10, so when they cancel each other out, I'm left with x plus 1. Hopefully you're seeing this quick pattern. Base of 4, base of 4. So what's left? X plus 1. Now this one, there is no exponent, so what I'm going to do is change. Since this is a base of 5, I'm going to change 25 into a base of 5. And I can make 25 into 5 by writing it as 5 squared. So when I'm done, base of 5 and base of 5 cancel each other out, and I get 2. So one thing that they didn't put, which I'm going to make another example, is just making this up. So again, I told you if the base and the argument is the same, you always get 1. So let's look at that a different way. So 3 to the what power makes 3. Again, that's 1. So that's another way to look at it. But if I want this problem to look like this is a log problem like this one. This is the better one, right? So log 3 is like log 4. 4 is like this 3, but this one doesn't have an exponent. So I could put a first power and that would still keep it as 3. So again, when this takes out this, you're just left with 1. So you can look at this one many different ways, but you're not left with nothing. You're always left with something, and that would be a 1. All right, we're going to not do the second section because this is a COVID year, and we're just going to leave that out. So that is our section on evaluating, or 6.2.